Hi, all of you. Thank you very much to be here with us to this 12th Railway Talk of the Union European of Railway Engineer Association. My name is Marco Corradini. I'm the secretary of the Union, and I'm pleased to welcome here to this talk. I remember that there's always the possibility to see also the previous talks because in our website they are registered, so you can see them. You can see also in my background which are our next activities, and the next talk, the 13th talk, will be about the Swiss Railway Operating Laboratory and will be at the end of March. As you can see, we are also planning a site visit in Italy, but at the moment it's all the positions are full. If you are interested, you can anyway write at the contact that you find on our webpage. So this evening we have a talk about friction management. We have two speakers. The first one is LB Foster, and the speaker are Jackie Butterfield and Volker Streim. And the second speaker comes from Virtual Vehicles and is Gerald Trummer. I remember that, as usual, the two speakers will do their presentation, and after the presentation, you have the possibility to put your questions. I would prefer if you speak directly, so raising your hands, and we will give you the words, or there's a possibility, if you prefer, to write in the chat. At the end, we will open the chat and read all the questions that you have put in it. So this was my short introduction, and I give then the words to Jackie Butterfield from LB Foster for this very interesting topic about friction management. Thank you, and Jackie, the floor is yours.
Thank you, Marco. Volker will start the presentation, so he will be our first speaker, and then I'll take over a bit later in the presentation.
Yeah, thank you, Marco. So welcome to the benefits of friction management presentation. Jackie and I split the presentation in two sections, and I will start with the first one now. In our presentation, we will talk about the reasons why we need to control friction. What are the problems with uncontrolled friction? What friction management is in our view as LB Foster, our approach to friction management with our customers. We also want to introduce some methods of application and the consumables related to them. At the end, we want to present some benefits that we documented over the last 25 years in case studies with customers from applied friction management. We as LB Foster are a global business specializing in friction management solutions for freight and transit. Our portfolio covers gauge phase grease lubrication units, top-of-rail units, onboard top-of-rail stray systems, and onboard sticks products, as well as the corresponding consumables. We also provide technical support and training, services, as well as engineering support through design work, system monitoring, and analysis. Why do we bother to control friction in the wheel-rail interface? The reason is very simple. With high friction levels, we experience noise from metal or metal grinding and see friction-induced damage appear on the rail as well as the wheels. Those damages are displayed in the first three pictures, and they bear great cost to the networks and also safety problems as low adhesion, as displayed in the fourth picture. We also associate higher fuel and energy consumption rates and poor riding quality with high levels of friction. The displayed table shows the optimal friction values from LB Foster's point of view when measured and tracked with a push tribometer, and also reflect what we aim for with our products applied to the top of the rail and the gauge phase. The figure shows the typical range of friction levels. Dry rails have high levels of friction around 0.7 to 0.5 μ, which leads to damage. Therefore, we need to control the friction to reduce the values from 0.7 to a range of 0.4 to 0.3 for the top of the rail. These so-called immediate levels of friction are high enough to enable traction and braking, while we don't see any more damages. To achieve those values, we use a pure water-based product called Caltrac. For the flange region, we aim for values of 0.2 to 0.1 mu. These values reduce friction in the flange region to reduce damages in this area for rail and wheels. Effective friction management requires two different types of products to allow coverage of all contact patches with the required friction values. As mentioned before, there is a lot of different benefits with an implemented friction management program. For example, wear reduction in the contact area, as well as delayed rolling contact fatigue and corrugation appearance. And also noise reduction and better fuel efficiency. An overview of issues can be reduced and mitigated with friction management is displayed on the slide. The overarching goal of any FIMMM program is to maximize the benefits. We, as LB Foster, have the philosophy of the solutions-based approach. This approach orientates at customer-specific circumstances. During the assessment, we try to identify issues and where they are, as well as how widespread these issues are. We also take information about the customer's network into consideration, like closed or open networks, and what kind of rolling stock is used in this. It is discussed if friction management can be realized as a trackside solution or if the customer prefers onboard solutions. We also take country or site-specific regulations into account, as well as the customer's budget to tailor a solution that fits the requirements. Once the friction management systems are implemented, we support management and maintenance of those systems and offer to perform long-term validation of the performance and generated benefits in form of reduced noise, improved wear rates, mitigated damages compared to friction management install times, to pre-friction management install times. In the table on the right-hand side, we can see what application options there are for the designated areas and what consumables are normally used in them. We assist in using the optimal equipment and consumables at the right locations and to maintain the equipment efficiently to generate validated results. After talking about our approach to friction management, we want to display a range of trackside solutions that we offer to achieve the goals. All of the equipment is designed and manufactured to comply with EN 15427. First off, we have a hydraulic gauge phase and check rail lubrication system called the PW. It applies a small amount of lubricant at each axle, passing over a small plunger mounted to the rail. Due to missing electronic components, further fine adjustment of the output rates is not possible. It networks with train speeds up to 100 km/h, predominant flange wear and noise issues, or wheel climbing. On a low budget, these PW units are a perfect fit. The highlighted yellow object is the product tank with the hydraulic pumping system. And at the rail we can see a pair of gauge phase bars. The activation plunger is mounted to the field side ahead of the unit. The electrical units come in a variety of shapes and sizes to fit the customer's requirements. With the integrated PLC, output rates can be adjusted by modifying them in terms of after how many axles we apply and how much in terms of pump run time. With the electrical units, the customer has also the option to use the remote performance monitoring options, which gives access to an online portal to see performance of each unit, as well as product levels and further details to reduce the workforce in track, reducing the site visits to the essential minimum. Our electrical systems have the option to use a variety of our application bars and therefore not limited to gauge phase and check rail lubrication, but can also be used to apply top of rail materials as well as traction enhancer products. With the wider range of products, as well as the option to adjust settings on the system, these systems are mandatory if a bespoke friction management strategy will be implemented. On the top left picture is a traction gel applicator, universal solar panel. Top right corner and bottom left corner show a P4 system, and the bottom right picture is a PXSL90 system. All systems come with the option of mains power, solar or wind turbine as a power source. All application bars are clamped to the rail and are adjustable to fit different height requirements in the networks. Application bars have various designs depending on the type of use. Gauge face and check rail bars, displayed in the two top pictures, come with multiple ports to allow better distribution of the grease along the contact area. Top of rail product bars, shown in the bottom left, have one center port or a small number of ports that distributes the product onto the top of the rail. Due to the lower viscosity of the top of rail materials compared to greases, the control of the output values is crucial to make sure that the friction values don't drop below the target values and to so avoid any negative impact on traction and braking. Application bars for traction enhancer gels, as shown on the bottom right, are made of more sturdy materials because they are used to apply abrasive materials to wheel rail interface. In addition to our trackside solutions, we also offer onboard solutions that are mounted directly to the rolling stock. This option reduces the amount of time in track and allows to maintain and refill the equipment in a depot. The first type of onboard friction management are the solid stick systems for both flange and thread. This is a purely mechanical system and uses a constant force spring to push the solid sticks against the wheel. The applicators are fitted with an interface plate, which is then fixed to the bogie frame of the vehicle via a mounting bracket. The system is self-regulating and requires no control system to operate. Solid sticks are clean, contain no liquids, and do not migrate from their position onto the wheel. The sticks form a layer of product onto the wheel, which builds up to saturation point in tangent track, and then when wheel flanging contact occurs, the lubricant or friction modifier transfers to the rail and is then picked up by the following wheels, and so not every axle needs to be fitted with applicators. The coefficient of friction achieved is different for the two types of sticks, with the front of flange and back of flange lubricant sticks highlighted in green, providing a coefficient of friction below 1.5 μ. Thread sticks highlighted in orange are formulated to give an intermediate coefficient of friction between 0.3 and 0.4 μ, thereby not interfering with traction or acceleration and braking. The second type of onboard friction management are spray systems. Wheel flange spray systems are widespread in the railway industry. Top of rail spray systems are not as common, but they also great benefits to protect the assets. Albie Foster developed a system called Caltrack Onboard, or short KOB, which sprays our purely water-based top of rail material onto the top of the rail, where it is picked up by the following wheels and creates a thin layer along the track. The KOB system can be directly connected to the TCMS system of the train. This direct connection is beneficial because the system is designed to apply a specific amount of product relative to the travel speed of the train at designated locations. Therefore, the product brought into the wheel-rail interface always meets the demands of the train and rebuilds the thin layer on the top of the rail to protect the rail and the wheels of following trains.
Thank you, Volker, for introducing our rationale for friction management, but also our equipment and hardware. So now I am going to talk a little bit about the consumables used in friction management and the required properties and characteristics. The consumables not only provide the coefficient of friction, but they also need certain properties in which to enable them to work in the equipment. So the next couple of slides, I'll just run through some key requirements of the consumables. So, and I apologise, I should have taken control there, but in terms of liquid consumables, all consumables, whether they're liquid or solid, need to deliver a low coefficient of friction. This is specified in the European standard EN 15427-2-1, which covers lubricant materials. And this should be a maximum of 0.15 at normal application levels. So the materials themselves need to have good film durability and provide wear protection, so that they need to last in the wheel rail interface. They also need to have effective carry down and transfer from the wheels to the rail and then along the rails. And also it is vital that they have low environmental and health and safety impact on operators. They should also have good product stability and consistent properties from batch to batch. Specifically liquid lubricants, they should have a low bar clogging properties, so that we don't want them to clog up the applicator bars. Otherwise, obviously, you're not going to be effectively lubricating the rail. The top picture you can see there is an applicator bar installed in track. It's been there for some time, but you can see that the grease is actually the lighter colour, and you can only see that there's only one port open on the applicator bar. So of the 16 ports, only one is applying grease. So obviously that's going to have a big impact on the effectiveness of that bar and the amount of grease that is going to lubricate the rail. The greases should have good column strength, and what we mean by that is that when the grease is pumped out of the bar, it rises up to a level which enables it to be picked up by the wheel flanges and carried down. So the image bottom middle left shows you an applicator bar, and you can see that the grease there is evenly spread across all of the 16 outlet ports and is a good height, so that when the wheel flange passes over, it will pick up the maximum amount of grease and carry it down the track. Greases should also have optimized pumpability and be able to be pumped at a range of operating temperatures, from minus temperatures, very, very cold temperatures, -20, -25 Celsius, up to +40, +50, where you're using them in maybe Middle Eastern countries or in Africa or desert regions where you get very, very high temperatures. Greases should have low oil separation. The picture middle right shows you grease in a tank which has clearly separated, and all the oil is left, and you're just left with the solid residue in the tank. And obviously this will not pump effectively through the unit, and so this should be avoided. And greases should have good adhesion to the rail and resistance to water wash off. In terms of solid lubricants, they should have good mechanical strength and thermal stability, as temperatures in the wheel rail interface can get very high, up to 300 to 400 degrees Celsius, and even higher with tread brake vehicles. The consumption rate should be optimized, and they should have a good interlock design so that the sticks do not fall out of the applicator onto the track and waste material. Similarly, top of rail materials have a similar set of key specifications, but in this case they should yield an intermediate level of friction, so that level of between 0.3 and 0.4 that Volker spoke about. Ideally, they should show positive friction characteristics, and what we mean by that is that the level of friction with increasing creep forces should be an increasing gradient and not fall off after the friction saturation point. This enables them to be very effective against such issues as top of rail squeal noise and also corrugation damage. They should not interfere with the safe operations of the railway in terms of traction, braking and or signalling operation. Again, they should have good durability in carry down and low environmental and health impact and should be stable. Liquid consumables should be pumpable and across the entire operating temperature range, and they should also be resistant to water wash off. Solid materials, again, should have good mechanical strength and thermal stability. So the pictures we have here, top is a top of rail material in an embedded rail application on a tram system. And you can see the top of rail material is flowing freely over the top of the rail and effectively covering the rail head. The middle left picture is another top of rail material, but the bar is looks to be clogged with dried material. I should explain that the picture here is actually a third rail power system. So the rail nearest to the bottom of the image is actually the third DC power rail. The picture on the middle right is a product which is separated in the tank. So obviously, as with the grease, that may cause problems with the equipment in terms of the pump. And also clogging of the bars. And likewise, the pictures of the solid sticks, we have one that is melted on the right, and the middle picture has fractured under the high vibrations. With traction enhancer gels, these have their own unique set of properties. They should increase friction to as close to dry clean rail conditions as possible, and they should also effectively break down any leaf film or contaminant on the rail and remove it. They should have good film durability and carry down and be able to be pumped again over a wide range of operating temperatures, and should have good stable product stability and not separate in the product tank over time. So the benefits of using the traction enhancer gels really is obviously an operational and safety benefit. So you're enhancing the braking and traction, which leads to fewer station overruns, fewer risk of signals passed at danger, fewer low adhesion incidents, wheel flats, and ultimately collisions, as we have seen recently in the last few years in the UK. So on to the main point of this presentation is, what are the benefits of friction management? Why would you implement a friction management system? And so there are real tangible benefits to friction management, all of which can be translated into significant financial savings in terms of improved asset reliability, so fewer failures, fewer corrective action interventions required. Friction management can extend the asset life of the rail and the wheel, which will lead to lower life cycle costs for track infrastructure and rolling stock. Reduced emissions in terms of nuisance noise, vibration, and also reduced fuel and energy consumption, which obviously lowers the carbon footprint of the system. And then finally, enhanced safety in terms of lower risk of derailment and defects, and a better ride quality for passengers. So trying to put that into some numbers, the table shows some immediate or short-term benefits to friction management and also longer-term ones. So the shorter-term benefits are reduced wear. So we see reduced wear rates for both rail and wheel of between 25 and 60%, a reduction in high-frequency nuisance noise of between 5 and 10 decibels, enhanced safety, so a lower derailment risk due to wheel climb by lubricating the gauge face or wheel flange, and improved fuel economy of an average of between 3 and 5%. Longer term benefits are a reduced requirement for grinding, remedial grinding or milling of up to 50%, reduced rail defects, in terms of rolling contact fatigue, cracks or spalling or corrugation, reduced fastener damage of up to 20 to 80% due to lower lateral forces in curving, and also an improved ride quality due to the improved vehicle steering. So the payback or return on investment of a friction management system can be as little as a year or less, but savings will be different for every system because every system is unique and has its own unique set of circumstances and issues. So I'll just go through a short number of case studies where we've seen real benefit in terms of improvement and reduction of damage. So the first case study is on rail wear reduction, and this is due to a trackside application of our Keltrack water-based friction modifier, applying that to a top of rail. So this is an example from the Port Authority Transit in Pittsburgh using Siemens rolling stock. So this particular line had an annual traffic level of 11.6 million gross tonnes, and the site in question was a 91 metre radius curve, 122 metres in length on a slight downhill gradient. So we applied Keltrack trackside transit product to the rail ahead of the curve, and the graph shows the reduction in rail wear experienced with using the system. So the graph at the bottom right shows you the reduction in head wear, gauge face wear, and also gauge corner wear. So you can see there's a significant reduction, particularly in the gauge corner wear. So that's around 75% reduction. The gauge face wear is around 55% reduction. The second case study is an onboard example. So this is from Prague Metro, where our onboard solid sticks are fitted to all three of the metro lines, A, B, and C. This case study goes right back to the mid-1990s, where the sticks were first fitted onto line B in 1996 and then onto the other two lines in 1997. So by fitting the wheel flange lubrication sticks, the wheel life went from 150,000 kilometres from new wheel to scrap wheel, and that increased to 800,000 kilometres wheel life. Following that, they introduced the tread sticks, as Volker described, onto line C in 2001. And by doing that, the wheel life then increased up to 1.5 million kilometres by reducing the tread wear and tread hollowing issues. Prague Metro also saw a 3 to 4% reduction in electricity costs on line C, and also a reduction in the rail corrugation damage growth as well, and an improved ride quality by reducing the vehicle hunting. To bring this case study right up to date, following the success of this, the other two lines, A and B, were fitted with the tread sticks last year. The third case study is on noise reduction. So this is again an application of Keltrack water-based friction modifier, and this is the Circumvesuviana line in Italy. So this is a 90 metre radius curve, 70 metre length on a level gradient. The vehicles also had onboard wheel flange lubrications fitted as well, but we applied the Keltrack directly to the track through an electric unit just ahead of the curve. And the graph on the right shows you the noise spectrum of obviously the sound pressure levels of the noise generated from that curve. So the red is the baseline measurements without the Keltrack. So you can see in terms of the high frequency portion, there is a characteristic peak at around 3 kilohertz, which is indicative of a top of rail squeal noise. And by applying the Keltrack, this has eliminated those peaks and significantly reduced the high friction portion of the noise spectrum. And then the final case study is a cost benefit analysis. So this is putting it in terms of in terms of euro savings in this case. And this is an example from the Canadian National Railroad in obviously in Canada. And this is a study done on one subdivision on that line, which is the Clearwater subdivision. So this is 139 miles, sorry, long section with an annual traffic level of 104 million gross tons and around 14,000 daily axle passes on the line. So very, very heavy traffic. So in order to calculate the cost benefit of the lubricator units in this case, the average distance between two consecutive units was calculated as the kind of baseline measurement, and this worked out at just over a mile between units. They then calculated the average wear rates measured from 15 separate curves and compared the curves with no lubrication versus lubrication to get the wear rate, and then from the wear rate they calculated the incremental cost of that rail per day. So this is a cost of replacing the rail, but prorated against the life of the rail. So each day that the rail is in operation, the wear is costing €588.74. So this is what it's costing the railroad. So if you multiply that by the average distance between lubricator units, this comes out at a cost of around €700. So if you then offset the cost of operating the units, then the net cost or the net saving of operating gauge face units on that particular curve in that particular subdivision is around €613. So that is the cost of not having lubrication. Those costs do not include loss of revenue. It's purely the cost of replacing the rail and the manpower and equipment to do the replacement. So if you would add into that the loss of revenue by having the network down to do the replacement, then obviously that cost saving is going to be much, much more. I'm not going to talk through the next two slides because it's just really to illustrate the range of savings that can be achieved through friction management, and to illustrate that we've collected a lot of data over the last 25 to 30 years that is kind of real life, real time data that proves the benefit of friction management. So this one is on rail wear savings. All of these references are publicly available, either papers from conferences or peer-reviewed journals. So they're all available to download or to view, or if you want copies of any of them, then please contact us. And then likewise, in terms of fuel savings, these are real fuel savings from railroads around the world, bringing it right up to date. So we have some from China from 2023, and a lot of heavy freight data from North America. So in summary, Volker explained that uncontrolled friction can lead to damage, noise, and safety issues. Different areas of the rail and wheel require different friction levels and therefore different products. We use a solutions-based approach which optimizes the friction management regime, and that involves assessing the issue, implementing the solution, managing the system by effective maintenance and filling, verifying the performance to make sure that you're getting the right benefits, and also long-term monitoring to make sure that you just close that feedback loop and you can make the changes and adjust the friction management regime as times change, or if circumstances change, or if even regulatory requirements change. And effective friction management can yield real benefits in terms of reduction in damage, noise, and energy requirements. Thank you for listening to our part of the presentation. I will stop sharing now and Gerald will share his presentation.
Yeah, good evening, everybody. My name is Gerald Trummer, and I'd like to talk about the simulation of friction management in railway operations. I hope you can all see my screen. The content of my presentation will be as follows. I'd like to give a brief introduction, talk about boundary conditions and challenges of the simulation of friction management or the evolution of the wheel-rail interface friction in operational scenarios, briefly present you the simulation model that we have developed at Virtual Vehicle, show you one result, one use case, and finally end the presentation with a summary, conclusions, and a brief outlook. A few words about the Virtual Vehicle Research GmbH. We are a research company that is located in Graz, in Austria. And we are around 300 people that work on the domains of automotive, which is the majority of people, and some people also work on the domain of rail, plus on other domains that are listed below. The working group where I'm working in is the group that deals with vehicle track interaction. So we work on topics of wheel-rail interaction and deterioration phenomena. We work on the topic of vehicle dynamics and operation analysis, on the topic of monitoring and diagnosis, as well as on the topic of digital twins network. If you now zoom into the wheel-rail interaction and deterioration phenomena, we have projects, and we had projects and published work about damage and deterioration that includes rolling contact fatigue, wear, and track settlement, for example. We work on material modeling, especially on severe plastic deformation of pelitic steels. So this is the material that you find near the surface of rolling contacts. We work on thermal phase change, so the formation of wide edging layer, but also on the behavior of ballast within a DM simulations, for example. We also look at the wheel-rail contact, work on the topic of creep force curves, creep force modeling, adhesion, and how third body layers influence the coefficient of friction. And finally, some of my colleagues work on the topics of noise and vibrations. But let's come to the topic, the key topic of my presentation, the friction management of the wheel-rail interface. It has a long history in railway operations. Sanding is done very frequently in railway operations. You can also apply traction enhancing products, and the aim is of these products to increase the coefficient of friction to higher levels. If you apply top of rail friction management products, you usually want to reduce the coefficient of friction from high friction levels to intermediate friction levels. This is done by using water-based products, but there are also oil-based or grease-based or hybrid products on the market. And finally, gauge phase lubrication is applied frequently to achieve a very low coefficient of friction to minimize wear. I'd like to focus on the wayside application of top-of-rail friction management products in my presentation. You see here a number of images on this slide from papers from the literature, how the application unit looks like and how these products are delivered to the rail surface. So usually this top-of-rail products are delivered to the rail as a puddle, and then the wheels roll through these puddles and need to pick up this product and carry it down the track. If we want to now simulate a railway an operating scenario and predict the wheel-rail interface friction for such scenarios, we face a number of challenges. First of all, of course, how the friction level develops and what friction level you get depends on the friction management product itself, on the lubrication properties, and also on the degradation properties. But for an operating scenario, you also need to take the contact conditions between the wheel and rail into account in terms of the contact pressure, the tangential stresses, the contact locations on wheel and rail, as well as how the product transfers between surfaces. As I said before, the product is picked up by the wheels and is redeposited to the rail surface by the wheel as the wheel travels along the track. As we heard in the presentation of L.B. Foster, we have different possibilities to apply the product. This can be wayside application units, but also onboard solutions exist. And you have a range of strategies, where to apply, how much to apply, and how frequent to apply. And because it's an open tribologic system, the local railhead conditions, so the environmental conditions, play a role. There are daily variations due to the weather, but also seasonal variations due to summer and winter. And of course, it's different if you run a railway in Scandinavia compared to running a railway in Spain, for example. Surface topography is expected to have an influence, as well as contaminations, and the term contaminations is here used very broadly. You may think of water. If it rains, that changes or may change the frictional properties of the friction management products. But also you may get influence that comes from, for example, gauge phase lubrication products that are present at the top of rail. To summarize, we have an open tribological system with varying boundary conditions, and this makes the prediction of the friction condition for operating conditions quite challenging. Let's have a look on some of those points. On this slide, you see results of product degradation testing. These are experimental results from twin disc experiments that have been carried out at the University of Sheffield. This is such experiments are frequently used to investigate the degradation properties of products. You apply product to the discs. These product applications are indicated here by these arrows on the top. And then you look on how the coefficient of traction recovers with increasing number of disc revolutions. And you see differences in this recovery process if you change the normal pressure, if you change the slip, and if you change the product amount that you apply. Another experiment that we carried out, or that our colleagues at the University of Sheffield carried out, is our experiments related to the product pickup. So you see here the outline of an experiment where a product is applied to the rail surface, and then a wheel is rolled over this puddle and is picking up the product. And you can do that several times. And at the end of the experiment, this product is removed from the surfaces and the product amount is weighed. And by that, we could investigate how much product is actually picked up by the wheel in this case. The key observation is if you have a little product on the surface, on the rail, for example, and the product is dry, there's a little product transfer to detect. If you have a lot of product and the product is liquid, then product transfer is much more taking place. I especially like this publication from the University of British Columbia. They investigated in the lab here what happens if you apply a puddle to a surface and then you roll through this puddle. You see an image on the left side. The colors in this image actually show you the product height on a surface. In the center, you see this blue line. That's actually the contact area of the wheel that traveled through this puddle. And what you see is the product is squeezed out of the center of the contact area in this case. Then you see this near contact area where you see varying product height. And if you investigate this region closer, you find out that this product height is approximately half of the gap height near the contact area. So we need to assume that the other half of the product has been transferred to the rail, to the wheel in this case. The same group also investigated how friction management product distributes in the field with the same technique. So in field trials, they measured the amount of product on the railhead just right after the application site, where you see a similar behavior. In the contact band itself, there is little product visible. Beside the contact batch, you have much more product. In this case, they found product up to around 100 meters from the application site. But you have to keep in mind that we are looking here only on the rail surface. And the detection limit of this method was around 3 micrometers. So product heights less than 3 micrometers are not visible here in this investigation. But as we have heard in the presentation of LP Foster, the carry-on distance of products is much higher. And how this can happen is shown on this slide here. This is a study from Sweden, where they applied top-of-rail products on the railhead, and they rolled over this area with a locomotive. And what they saw is that quite a significant amount of product is sticking to the edges of the contact band on the wheel. And this is exactly the mechanism that we think is important to carry on the product over large distances in operation. Yeah, local railhead conditions, the environment. On this slide, you see experimental data from Australia, where they measured the ambient temperature, the green curve, and the rail temperature, as the red curve, in spring, an Australian spring. So the ambient temperature was roughly 34 degrees Celsius. And at the same time, so it was a sunny day, and at the same time, the surface temperature of the railhead reached temperatures of 55 degrees Celsius. So this is something to keep in mind, that the surface temperatures of the railhead might be significantly higher than the ambient temperature. I've included here data about weather station data from weather station that is north of Stockholm. And I have investigated here what are the relative humidity and temperature conditions over a period of 4 years. And based on this data, I try to predict then the local railhead conditions, taking into account the solar radiation. And the outcome is very similar as in the case of the data set of Australia in the slide before. On sunny days, the surface of the rail is usually warmer and drier than the surrounding air. You can see that in those two diagrams if you carefully check the color in the red circle. On the left side in the weather station data, you see almost no data points, whereas in the right diagram, you see that these conditions occur in reality. The surface topography also has is expected to have an influence on the frictional properties. Usually, the surface roughness is not well known in operation, and it is expected to depend on the operating conditions, on the maintenance conditions. However, this study from the railway in Sweden shows that after grinding, the surface roughness of the rail reduced quite quickly to a level of 1 micrometer SA within less than 2 days. Yeah. If we now want to predict the coefficient of friction in the wheel-rail interface, we have to take those boundary conditions into account. In our projects, we have built a simulation model that aims to predict, or that predicts, the wheel-rail interface friction for operational scenarios, and it should work for different top-of-rail friction management products. And the key features of this model that we think are important are: we use realistic operational contact loading conditions. This information comes from multi-body dynamic simulations of railway vehicles. So each individual axle of the railway vehicle, for example, the leading axle and or the trailing axle, has its characteristic contact conditions that vary along the track, and this is considered in our model. The model is able to or works for an arbitrary track layout, so we can specify a track based on the track curvature that consists of tangent track, transition curves, and curves. And we included a detailed modeling of how the product degrades and spreads on the surfaces of the wheels and the rails in operation. It is, I think, computationally efficient, as it runs on my laptop computer usually. And we are currently working on the influence of the ambient temperature and humidity on the wheel-rail interface friction. Actually, we have two simulation approaches or two variants of our friction prediction model. I'll start on the left side with the model I called, or I termed here, offline calculation. This is the friction prediction model that is implemented in MATLAB, and essentially it post-processes contact patch data that is supplied to the model as an input. So this contact patch data or information comes from MPD simulations, as said before. It is computationally very efficient, as it allows the calculation of, let's say, 10,000 wheel passes for a specific curving scenario on a laptop computer. And I think it's well suited to investigate steady state friction conditions and to test or compare different product application strategies. On the other hand, we have now a model available that integrates directly as a user function in the multi-body dynamics simulation software SIMPAC. This is what I called online calculation. The advantage of this approach is that we have now full coupling between the friction condition in the wheel rail interface with the vehicle dynamics. So if the coefficient of friction changes, this influences the contact forces directly, and SIMPAC needs to make sure that everything is in equilibrium. Of course, this is computationally much more expensive because you have to simulate a whole railway vehicle. And you can thus achieve only a lower number of wheel passes, but nevertheless, you can carry out very detailed studies of product pickup and carry down behavior and how this influences the vehicle dynamics. So this is a drawing of the key mechanisms that we consider in our model. The first top of this diagram, you see a product applied to the rail surface and a wheel that's just before the wayside application area. The wheel picks up, as said before, the product, redeposits it to the rail surface after the application site. If you continue, if several wheels pass, the product amount will reduce gradually. And after some time, it will be necessary to reapply product at the application site, because the target is of friction management to keep the friction level in some intermediate level. So this is where the model can help, because with this model we have a tool to investigate how the amount of friction management product and the position of the applied product influences the coefficient of friction along the track, how it is carried along, how the product is carried along the track, and how this coefficient of friction changes with the number of wheel passes. This slide is about the lateral dimension of the problem. So as said before, it is important to consider the lateral position of the contact patch on the surfaces of wheel and rail. Those vary constantly if a vehicle travels along the track. We consider this in the model, and we also consider, of course, the product transfer in the contact area, as well as product transfer in the gap outside of the contact patch. This is a drawing of the model discretization. So we have a 2D discretization of the rail surface, and in a similar way, we have discretized the surface of the wheel. each of the element to each of these elements, the product height is assigned, and if the contact batch touches or overlaps with these elements, this product amounts get updated in the model depending on the operating conditions. As a use case, I'd like to show you simulations that I've carried out for data that I found in literature. So Daniel Szablewski published data of testing of friction modification materials at the fast test ring at TTC in Pueblo in Colorado, US. In 2015, and he published information about friction turbometer measurements, so friction data, and lateral force measurements for varying product application rates. So I tried to rebuild this experimental setup in my simulation. You see in the bottom diagram that the layout of the track. On the left side is the top of rail application, the wayside application unit, and at the distance of 884 meters from the application site, there is this lateral force measurement site, and this is the site also where the turbometer measurements have been carried out. This is a typical output of our simulation model. This can be confusing if you see it the first time, but I'd like to start slowly with the top of this diagram, or this diagrams. On the top of the diagram, you see the track layout. So this is the track curvature as a function of distance. You see that we first enter a right-hand curve, followed by a tangent track, and then we enter a left-hand curve. If we go to the bottom diagram, this shows the distribution of friction management product or top of rail product on the rail surface. So horizontal axis is distance from the application site, and the vertical distance is the lateral position on the rail surface. The wayside application location is highlighted here in blue on the left side. The red lines you see, this is the boundary of the contact patch of this particular wheel that I show you here in this diagram, and you can see that the location, the lateral location of this of the contact patch on the rail side changes depending on where you are along the track. And this is an input that comes from MBS simulations. The middle diagram shows you the condition on the wheel surface. So for the corresponding track position, or at the corresponding track position. So this is somehow the time evolution of the surface condition on the wheel. And similar as on the rail side, you have the contact patch that's varying as you travel along the track. So what is important in this diagram is the following. If you look at the middle diagram, you see here that at the wayside application location, there is product picked up by the wheel, both inside the contact area and outside the contact area. And this product that is picked up outside of the contact area stays on the wheel surface for a very long time. Just before the lateral force measurement site, and before the measurement site, actually the contact patch enters the surface area where this product is stored. So this is a very important mechanism that we consider here in our model. Why this is important is illustrated in this slide here. On the right side, you see a diagram with 4 curves. The thin lines are experimental data from the paper of Schablewski, which show you the coefficient of friction as a function of the product application rate. And the thick lines are actual simulations with our model. I've included here 2 variants of the simulation. The thick solid line shows you the results of simulations where product pickup by the wheel outside of the contact patch is included in the simulation, whereas in the for the results with the dashed line, this mechanism or this pickup by the wheel outside of the contact patch has been disabled. And as you can see, the predicted friction levels agree much better with the lateral force measurement data if you include this mechanism in the simulation. And the results in general highlight the importance of this pickup and carry on mechanism to predict the coefficient of friction in an operational scenario. This brings me already to the summary and conclusion. So I've shown you that we have developed a simulation model that is able to predict the evolution of the wheel-rail interface friction for operational scenarios when top-of-rail wayside friction management products are applied. This model covers important aspects from our point of view. That includes, it works for arbitrary track layouts. It uses realistic contact loading conditions. It considers laterally changing contact patch positions along the track. And it includes a detailed modeling of how the product transfers between the surfaces of wheel and rail in terms of pickup of product and redeposition of product to the rail surface. Again, I have shown you the capabilities of this simulation model for one literature use case briefly. And in general, I think this simulation is a powerful tool to investigate the effects of top-of-rail friction management on wheel-rail interface friction with respect to different application methods, whether it is wayside or onboard, for example. You could investigate different application frequencies, investigate different application amounts, and carry out simulations for different track layouts and as well as for different traffic conditions. Work in progress includes the consideration of the influence of the ambient conditions in these simulations. And we will carry out in one of our running projects model validation through track testing. But this is, of course, an important thing. So we are interested to validate and improve the simulation model for a broad range of operating conditions. So if you're, for example, a product supplier or a railway operator and you like to have a closer look on how friction management products work for a specific scenario, or if you can even provide experimental friction data from operations, then we would be, of course, highly interested, and then please let me know. And with that, I'd like to thank you for your attention, and I'd like to hand the control back to Mr. Corradini. Thank you.
Thank you very much. I think that I want to thank the three speakers because their presentation were very in depth and this topic is very important in the railway operation. So thank you very much for your contribute to our world. As I've said at the beginning, if there are questions, you can raise your hand, and I start with a question from me, because it seems that these products, this improvement that are done in this field, in this application, are very good, but there's a point that maybe I'm wrong, but I didn't hear in the presentations. And if you put the product on the rail, on the surface, there could be the possibility that with the monitoring of the rails, of the defects, it's not possible to see these defects. This is a point that from the beginning of the modern railways has to do with the railwaymen, and I want to hear from you if the products that you have mentioned are suitable for for a convenient monitoring of the railway tracks. Thank you very much.
Yeah, thank you, Marco. The short answer is yes, they are compatible. Obviously, if you're applying any sort of layer to a rail or even to a wheel, you're creating a barrier between the wheel and the rail. So in terms of top of rail materials, we have tested our materials to ensure that they will not interfere with things like ultrasonic or eddy current testing for looking for defects in the rail. I can't speak to the other products that are on the market that L.B. Foster don't produce. Likewise with gauge face greases, they don't tend to interfere with obviously eddy current ultrasonic testing, but obviously they can interfere with visual examination and any sort of optical examination techniques. So if you are doing kind of optical measurement techniques, then particularly gauge face greases might cause a problem. But obviously the products are there to prevent the defects that you're looking for from happening. So there's got to be a balance there. But yeah, it's a very, very good question.
Thank you. So, because we have heard from many advantages from these products, but there are also some disadvantages that, of course, we have to take in account. Okay, thank you very much for your reply. And I don't know if there's another question from the public. I don't see any raise.
There's a few in the chat.
Few in the chat. I don't.
Yeah.
Okay. Thank you. So, because it's not possible for me to read this one. There's one from Hansen Lasse. Which component should wear out more easily and is therefore designed to be softer? The wheel or the rail? There are different philosophies in Europe, aren't there? Which is more economical from your point of view? A softer, faster wearing wheel or rail?
So from our point of view, we would say that the wheels should wear out easier, but mainly because swapping wheel sets can be done at a depot without blocking the whole track during that time. Therefore, we would not miss out on any revenue from other trains using the same track during that replacement time. But in general, I think it always depends to the people. If they're track guys, they would say, oh, wheel sets need to wear out quicker. And if you're like rolling stock person, you would say, oh, I would say the track should wear out quicker so I don't have the work in my hands. So it really is like a complicated philosophy question depending on which side of the river you are.
Thank you. I hope that we have replied in the right way to Mr. Lansen. Hansen. And another one question from Metodi Atasanov is could we manage predict friction between rail and wheel by measuring equivalent conicity?
Gerald, do you want
Should
to
I repeat? No.
No,
Yeah,
do
probably
you want to
Mr.
take that one?
Atanasov could elaborate a little bit more on his thoughts.
I would suggest
Usually,
if
the main approach that we use to record the friction is through tribometer measurements, because those tribometer measurements can be used. Well, these tribometers can be used quite flexibly along the track, so they can record whole profiles along a track, as well as record the friction at different locations along the track for different at different times. Yeah, if you want to. So this is the key measurement technique I'm familiar with. I haven't thought about predict friction through the equivalent conicity.
Yeah, I think equivalent conicity, obviously it's a calculation, but what it won't take into consideration is what is in the third body. So I think, correct me if I'm wrong, Gerald, it's the calculation is based on T gamma values. So friction comes into that, but in a real life situation, you will never know exactly the composition of the third body layer and therefore what the base levels of friction will be. So in part, you could maybe predict to some extent, but I don't think you could do it accurately. Not in a kind of real world situation.
Do you want to add something, Gerald? Because
No.
you're thinking. Okay.
I'm always thinking, yeah.
Okay.
Yeah.
Thank you. So we go to the next question from Simon Eftimov. May we make a conclusion that combination of different friction management products will have a synergy effect and will be the optimal solution for the philosophic rail wheel conflict?
Yes, I think the answer is yes. Different friction management products working together will have a synergistic effect, but you always need to take into consideration the type of materials and how they will interact. So, for example, a combination of a gauge face and a top of rail application will give you the maximum benefits in terms of reducing the damage mechanisms. However, from a practical point of view, you wouldn't really want to apply a gauge face material in exactly the same position as a top of rail material, mainly because of the risk of the two materials combining together. So what I'm talking about is if you get gauge face grease then contaminating a top of rail material, then you run the risk of actually having a too low adhesion or coefficient of friction. So for that reason, and in the UK, Network Rail, as the infrastructure manager, have certain rules there to have a set spacing between different applications. So you would have at least 20 to 30 meters between a gauge face application and a top of rail application, so that you would prevent any cross contamination of the materials, which might lead to a risk of low adhesion on the top of the rail. But yeah, if you combine the two, and likewise an onboard system combined with a trackside system, we have many such examples in the UK where the two systems are working together to give you the maximum benefit. So in answer, yes, Simeon, you can conclude that. You've got a second bit of the question. Yeah, asking whether friction management is equally efficient in application to standard profile and reprofiled rails. Volker, do you want to take that one, or do you want me to carry on?
Oh, I can take that one. So the quick answer here is also yes, but mainly because we can adjust the bars to distribute product into the contact patches. So we can meet the changes in the rail height after reprofiling those rails.
And the same applies to an onboard, certainly to the solid sticks. So the solid stick applicators are aligned to a specific position on the wheel, and they are adjustable so that as the wheels wear, you can adjust that position of the applicator so that it's always in the optimum position for applying the lubricant or the friction modifier to the wheel tread.
Okay, thank you very much. Then there's a question from Mr. Shogang. You model the friction management as a third BL in the model, and how about the material model and creepage COF relationship? Coefficient friction.
We do not model the third body layer explicitly in our model because for reasons of computational efficiency. What is included in the model is actually we have the product height as an internal model variable. The local product height is the key internal model variable, and this local product height is changed by a consumption function, per wheel pass. And this consumption function depends on the contact conditions, for example, and of course of the material degradation properties of the product. And of course, there is a relationship between the local product height, the average product height in the contact patch, and the resulting coefficient of adhesion. And this relationship is tuned to or has been parameterized based on experimental results, mainly based on data from twin disk experiments.
Okay, thank you. Then reading the other comments, there are many compliments to the speakers because I think that you have presented very good this topic. And there's another comment from Mr. Six. I want to read it because he writes that equivalent conicity has nothing to do with friction. It's a poor geometric quantity. So he has given another input to the question of before. Okay, so we are at the end. If there are no other questions, I thank all the speakers again. I thank the public to have been with us all this time. And I want to remember that we will have another EURAIL talk at the end of March, so in springs. And it will be about the Eisenbahn Betriebslabor in the Schweiz. And okay, so with these words, I wish you a good evening if you are in Europe, or a good day if you are abroad in the world. Thank you very much, and goodbye.
Thank you.
Thank you.
Bye-bye.
Thank you.
Thank you.